SwayamPrabha. Digital India. Educated India.
In this lecture, let us discuss about supersonic and hypersonic shock interactions. We will begin our discussion with shock diamond formation in overexpanded nozzles. So, if you recall, in week 11 the first lecture covered detailing on nozzles both for supersonic and hypersonic applications. And today we are going to discuss an interesting phenomena of shock diamond when you have an overexpanded nozzle. Followed by that, we will learn about the pressure deflection diagram, and then we will try to cover shock-shock interaction. We recapitulate some of the important relations for isentropic flow through CD nozzle. We remember about the area velocity relation, and we know that how a supersonic nozzle and supersonic diffuser functions. In a supersonic nozzle, we have an accelerating flow starting from subsonic conditions, reaching sonic condition at the throat, followed by supersonic acceleration in the diverging portion. While in a supersonic diffuser, a supersonic flow comes in, decelerates, becomes sonic at the throat, followed by subsonic deceleration in the diverging portion. We also learnt about the area Mach number relation, and if you recall, in this week's lecture we have used the area Mach number relation quite elaborately when we looked at nozzles for a prospective supersonic as well as hypersonic application. And we also have the definition for M star, which is based on the throat condition A star. So, Mach number at any location in the duct is a function of the ratio of local duct area to the sonic throat area. And we talked about mass flow rate through the CD nozzle under choked condition, and in this equation you see that M star has been written in terms of the star conditions. The rho star, U star, T star values have also been mentioned. So, if you are not recalling these relations very clearly at this point, so it may be a good time for you to go back to earlier lectures and recapitulate all these relations. We further remember that following the isentropic relations at m equal to 1 for a calorically perfect gas, how to calculate the P by P naught, T by T naught at the throat. With that, we move on and we try to talk about a situation like this, where you have different back pressures imposed at the outlet of the nozzle, and when you have different back pressures, different conditions may exist in the diverging portion of the nozzle. You could have a perfect expansion to supersonic conditions, while the flow may become subsonic when the back pressure is considerably large and it just reaches sonic condition at the throat and then becomes subsonic. It may be that it accelerates for some length along the nozzle, and then there is a normal shock formed inside the nozzle in the diverging portion, and there is a subsonic flow thereafter. There could be other situations too. We have tried to indicate it here, that you can have a situation where there could be under expansion of the flow, which is produced by a pressure which is even lower than the perfect expansion which is expressed by PEI, where the flow isentropically expands all through the length of the nozzle and exits exactly with the same pressure as that of the back pressure. That means, the exit plane pressure and the back pressure are identical, and under expanded flow would mean that you have a situation where the back pressure is even lower than what pressure you have at the exit plane, and therefore, you have a situation where there is prospect for further expansion of the flow. And then there are other situations like where you have a pressure like PE6 marked here, where it is an over expanded flow produced which is producing oblique shocks at the exit. A PE5 pressure on the other hand will create a normal shock right at the exit of the nozzle. So, when you have over expansion, then you ought to have some oblique shocks formed at the exit of the nozzle in order to adjust with the back pressure, and that is very often encountered in the study of nozzle flows, because you design a nozzle for a particular back pressure situation, but very often that nozzle would have to operate at different conditions where the back pressure varies. For example, the nozzle which is functioning to lift off a rocket has to go through altitude change, and therefore, the ambient pressure will change. It will keep reducing monotonically as the rocket gains altitude, and then as it gains altitude the back pressure keeps on reducing, and therefore, the nozzle will most often be functioning at off design conditions. So, such mismatches of exit plane pressure and back pressure is obviously going to happen, and in this case we are trying to explore a situation where oblique shock has formed at the exit of the nozzle, and we have a situation like this, a pair of oblique shocks coming out from the exit of the nozzle, and then we are going to explore what happens to the flow thereafter when we follow the waves further downstream. In order to explore that, we talk about the phenomena of wave reflection from a free boundary. So, based on the sketch of the over expanded flow that we saw in the last slide, the gas jet from the nozzle which exhausts in the atmosphere would have a boundary surface that would interface with the surrounding quiescent gas. There would be an issue of matching the pressure at the jet boundary, since the pressure inside the jet is not the same as that at the jet boundary. Now, what we are talking about is essentially a mismatch between the pressure that we have here and the pressure that lies outside, which is basically P infinity. Now, the pressure across this boundary has to be preserved, that is, the jet boundary pressure must be constant along its complete length. It is worth noting that this jet boundary is definitely not a solid one. So, we are not talking about a wall. It is a free fluid boundary that can change in size and direction, and therefore, let us see how that boundary, the fluid boundary, responds to the incident waves. The shock wave incident on a constant pressure boundary is the first thing that we will try looking at. So, you have an incident oblique shock which is coming and meeting a constant pressure boundary, and then we see that there is a reflection of that same wave, but this time it is reflecting in the form of an expansion wave, not as a compressive wave, a shock wave. So, what happens is that in region 1 the pressure is P infinity, which is of course equal to the surrounding atmosphere, and then comes this oblique shock and raises the pressure in region 2. Now, the pressure behind the oblique shock is definitely higher than P infinity. So, we note this inequality. However, at the edge of the jet boundary the pressure must always be P infinity. Therefore, when the incident shock hits the boundary, it must be reflected in such a fashion so as to obtain P infinity in the region 3. So, once the reflection has happened, you should be able to restore the P infinity back in region 3 behind the reflected shock wave. Now, since P infinity is less than P2, this reflected wave must be an expansion wave, so that this adjustment is possible. And across the expansion wave, the pressure P infinity is recovered in region 3. That means, gradually the pressure from P2 over here falls down through an isentropic expansion and reaches the P infinity pressure. So, if you imagine that this is pressure P2, you regain P infinity pressure here. So, once there was a step jump here when the oblique shock was crossed. So, there was a step jump here from P infinity to P2, and then there is a gradual reduction as it crosses the expansion fan back to P infinity through this incident and reflected waves forming that region, where the incident wave was a compressive wave, while the reflected wave is an expansive one. As a consequence of this, the flow is deflected upward by both the incident shock as well as the reflected expansion wave. So, we take note that the flow is kind of moving upwards here through this region. This is a very interesting phenomena, which is complemented by another case where you have an expansion wave incident on a constant pressure boundary. We have to realize that in the earlier figure, if you have an incident shock which might have come from a situation like this, later on it reflects back as an expansion wave, and then what would happen is that this expansion wave will cross the center line of the jet and move over to the other side, while the expansion fan which forms from the lower side comes back to the upper side, and we are having a look at such an expansion fan here which has come to the upper side. Now, when it is incident on that constant pressure boundary, what we find is this time it reflects back in the form of an oblique shock. So, this is an oblique shock which is formed when the reflection takes place. Expansion waves emerge within the jet stream as a result of the incident oblique shock and the consequent reflected expansion wave. In the adjacent sketch, an expansion fan is reflected from a free boundary as a bunch of finite compression waves. So, a bunch is created which quickly coalesce into a single oblique shock wave. Therefore, based on the above discussion, we can conclude the following: that waves incident on a free boundary reflect in opposite manner, that is, a compression wave reflects as an expansion and an expansion wave reflects as a compression. Also note and keep in mind that waves incident on a solid boundary would reflect in like manner. So, a compression wave reflects as a compression wave, an expansion wave reflects as an expansion wave if it is a solid boundary. So, these two differences are extremely important and need to be kept in mind. What is the final consequence? We come to the supersonic overexpanded nozzle, the complete picture. We end up getting a diamond wave pattern in the exhaust of the nozzle. It is because of the similarity in the appearance that we have with cutout diamonds. In the case of an overexpanded nozzle flow, the flow pattern downstream will appear like the way we have sketched here. So, first it began with two oblique shocks approaching each other, refracting, then for the first time reaching the constant pressure boundaries, reflecting back as expansion waves. Those waves are refracting further in this region, then reaching the constant pressure boundary again, reflecting back as compressive waves, and this goes on alternately. Now, here we talked about an overexpanded nozzle flow. On the other hand, we could have had an underexpanded nozzle flow too. So, how would flow downstream of an underexpanded nozzle flow look like? So, try to think over it, try to sketch it, which is a homework for you. Let us move on to the next topic, where we discuss about pressure deflection diagram. We talk about two oblique shocks here, one over here, the other is over here. The one that is on the left is called as a left running oblique shock. We have the flow direction moving from the left towards the right, and if you are pointing downstream, you are moving along with the flow, then you find this wave to your left, you would find a wave like this to your right, moving away towards the right if it emanates from your location, and thereby the names that they attain. And you find, because of the kind of inclination that they have to the flow, a flow across the left running wave would tilt upwards, while the one along right running direction will tilt downwards. And we have a special diagram here which we call as the pressure deflection diagram, which gives us the locus of all possible static pressures behind an oblique shock wave as a function of deflection angle for a given upstream condition. So, if we imagine reflecting what we see in these two diagrams through the pressure deflection diagram, the pressure deflection diagram will look like the way we sketched here. So, it has a kind of lobe like structure. It looks somewhat similar to the theta beta m plot that you learnt about earlier. For different Mach numbers, you had plots looking like this, and that is kind of analogous in the sense that if you have higher theta, you are talking about higher beta, and you are also correspondingly talking about higher pressures. So, there is some kind of an analogy between the two. And here, for the two cases, we have a pressure deflection diagram drawn like this, where the point 1 represents the free stream condition, which is basically common for both. And from there, if you go towards the positive deflection, it is for the left running wave which tilts upwards. You have a positive theta, and you pick the correct theta which represents that angle theta 2, and you get the point 2, which correspondingly describes the pressure that is attained in region 2. Again, if theta 2 dash is negative of theta 2, then you will have a theta 2 dash represented first of all on the negative side, because the direction of deflection is just the other way around. So, it is a negative angle. Moreover, because of the symmetry and identical upstream condition, you will end up getting the same pressure rise, which is corresponding to the point 2 dash, where P 2 and P 2 dash are identical. Likewise, if you keep talking about different deflection angles, you would end up following this lobe. As long as you have attached oblique shocks, you will follow this lobe. That is basically the motivation behind representing deflection versus pressure changes across oblique shocks through a pressure deflection diagram. If you look for an example, you can talk about intersection of oblique shocks of opposite families, and then we have an interesting problem here. You have a channel through which you have a supersonic or a hypersonic flow moving downstream, and then you have two compression corners. As you may recall, in the earlier case, you had two changes of theta, one was positive, the other was negative. Similarly, this one is positive, the other one is negative. However, purposely we are talking about a situation where the magnitudes do not match, and this in the given situation, the theta 2 is greater than mod of theta 3, and as a consequence what happens is two shocks of opposite nature are created which are unequal in strength. So, first of all, they come from opposite families, in the sense one from the left running, the other from the right running families. The other is because the deflection angles are different, their strengths are also unequal, and therefore, you end up finding that the pressure deflection diagram has a different appearance compared to what we had before. And let us try to see what goes on over here. Further, as you may understand from the diagram here, that as the two shocks get created, they reach an intersection point and they refract beyond that intersection point, propagating in slightly different directions downstream, and then you find that the flow aligns in such a manner that streams which are joining from the two sides, one from the upper compression, the other from the lower compression sides, follow the same direction after the refraction occurs, and there seems to be a line over here which segregates the two, the regions 4 and 4 dash that we have marked over there, and we will try to explain what is going on there. There is a dividing streamline between the two regions which we call as the slip line. So, we can see it better in this view, and there are a few conditions that must hold across the slip line. The pressure must be the same, P4 should be equal to P4 dash, otherwise the slip line would be curved. The velocities in regions 4 and 4 dash must be in the same direction, although they are in general going to be different in magnitude. And additionally, because if you follow two different streamlines, crossing the two shocks would end up having two different entropy levels, there is difference in the entropy levels of the regions 4 and 4 dash. So, S4 and S4 dash are not identical. The pressure deflection diagrams help us to visualize this solution of shock interaction processes. The theta p diagram corresponding to M1 is drawn as the solid curve, that is the one we are talking about over here. The point 1 denotes conditions in region 1 ahead of the two oblique shocks. In region 2, the flow is deflected through the angle theta 2. Therefore, point 2 on the theta p diagram is located by moving along the curve until theta is equal to theta 2, and remember that this is a positive angle. At point 2, a new theta p diagram is drawn which corresponds to M2, because that is the Mach number that we are talking about downstream of the shock. The pressure in region 4 dash must lie on this curve. Somewhere on that curve the pressure 4 dash should be available, and similarly point 3 is located by moving along the solid curve until theta 3 is reached. So, that is here, and that is a negative value. This deflection is downward, hence we must move in the negative theta direction. Point 3 corresponds to region 3. At point 3, a new theta p diagram corresponding to M3 is drawn. So, that is the one we have over here. The pressure in region 4 must lie on this curve, and again there should be a point lying on these two curves for M2 and M3 where the pressures coincide, and we have found a common point over here where P4 is equal to P4 dash. The point corresponding to regions 4 and 4 dash is the intersection of the two dashed theta p diagrams. This point defines the flow direction, hence slip line direction in the regions 4 and 4 dash. So, that is how pressure deflection diagrams could be extremely useful in studying these kind of shock-shock interaction phenomena. We then move onwards to discuss about shock-shock interactions, and as an introduction we look at this very practical problem where we see a generic hypersonic vehicle showing shock-shock interaction in the vicinity of an engine cowling. Generally, we have the engines of these vehicles located in the bottom region. Many a times we talk about supersonic combustion ram jet engines used for these purposes. So, we call them as scramjet engines, and they are often located in the lower part of the body, and the engine cowling somewhere lies over here. The inlet shock from the leading edge of the vehicle, the nose region of the vehicle, which is going to propagate downstream, essentially meets the engine cowl, and that is the incident shock or IS marked over here. And then we have a blunt leading edge of the engine cowl, which gives rise to a cowl shock, which is basically a bow shock, and the incident shock meets the bow shock here, and different kinds of interactions are possible. We intend to discuss a bit about these kind of engines also later in the course, if we find a little time, with more orientation of the aerodynamic phenomena in such engines. Shock-shock interactions can occur on engine cowls and of course, also around blunt bodies. Here we are citing the example of a shock being incident on the bow shock formed on the engine cowl. In supersonic and hypersonic flow fields, shock waves impinge on each other, leading to shock-shock interactions. The ones that involve straight oblique shock waves are simpler to handle. We usually can use algebraic methods to solve for them, and again most often for supersonic cases we assume calorically perfect flow. For hypersonic conditions, if we need to account for the reactive flow calculations, understandably the calculations will become more complicated and they cannot be solved by such simple techniques. Most often we have to account for solving the governing partial differential equations. Therefore, such interactions, first of all because of the reactions and because where the shocks which interact with each other are curved or are more complex, we have a mixture of straight and curved shocks. In such cases, mixed subsonic supersonic flow is produced in the flow field, and such flows can be solved using CFD techniques, or they can be experimentally visualized using Schlieren or shadow graph, and therefore either computing or experimenting such flows are more complicated. Here for simplicity we are considering the interaction patterns which arise due to these shock-shock interactions to be inviscid in nature. Some hypersonic flight vehicles are adversely affected by the shock-shock interactions. If they are not mitigated appropriately, they can destroy parts of the vehicle and consequently the entire vehicle itself. One of the hypersonic vehicles which was affected by this kind of a flow is the X-43. In such vehicles, the oblique shock wave generated at the nose of the vehicle propagates downstream, reaching underneath the vehicle and impinges on the leading edge of the cowl of the scramjet engine, which propels the vehicle. The shock wave emanating from the nose is called as the inlet bow shock, because it is designed to impinge on the inlet cowl of the engine. This leads to efficient containment of the flow that enters the engine and prevents spillage of the flow. The inlet cowl is provided with a blunt leading edge. This helps to mitigate aerodynamic heating. Due to the blunt leading edge, a detached curved bow shock forms upstream of the cowl leading edge. This is more like the bow shock that develops near the stagnation region of blunt bodies. So, we once again recapitulated some of the facts. Additionally, we got some more information. Figure that we had seen earlier, we are revisiting it here, and we are revisiting it with a purpose. The shock from the nose of the vehicle does not impinge directly on the surface of the cowl, but rather on the cowl shock wave, and that is where the two shocks start interacting with each other. This sets up a rather complex shock-shock interaction that can change the nature of both the shocks and the surrounding flow field. The type 4 interaction is particularly interesting and important because it results in a supersonic jet that impinges on the engine cowl, creating large peaks in pressure and heat transfer on the cowl that can cause damage to the vehicle structure. So, it seems there are many types, and there is a type 4 which the designers of hypersonic air breathing vehicles have to be particularly careful about. The other types of shock interactions are typed as 1, 2, 3, 5 and 6. This 6 family of shock-shock interactions was first identified and studied and reported by a famous scientist Edney, and therefore, we often talk about the Edney shock-shock interaction. As I mentioned earlier, that we consider the flow to be inviscid, imagining it to be a viscous flow at high Reynolds number. The curved bow shock exists around, or rather exists around the blunt body, we will call it as BS, the bow shock. The sonic points which exist around the body will be called as SP. No shock-shock interaction would occur on the blunt body till a shock impinges on the bow shock with specific strength and angle, and that is what is going to be called as the incident shock IS. It would be interacting with the bow shock at a certain location, and this location makes a lot of difference on the type of the interaction. The resulting shock-shock interaction depends on where the impinging shock strikes the curved bow shock wave, and the bow shock is divided usually into 6 sectors labeled as 1 to 6. The impinging shock strikes the bow shock in sector 1, resulting in type 1 interaction. If it results in interaction in sector 2, it would be called as a type 2 interaction, and so on. So, there are more details on this, and a wonderful text to have more details on this is the Handbook of Compressible Aerodynamics by Dellery. We will discuss more on these details in the subsequent lecture. So, in this lecture we discussed about shock diamond formation in overexpanded nozzles. We learnt about pressure deflection diagram. We learnt about the 6 shock-shock interaction patterns. We just began the discussion on that. In the introductory part, we have developed some familiarity about it. We will complete that discussion in the next lecture. Thank you.